who is Professor Tatsuo Iguchi from Keio University, Japan, and you will speak about Isobe-Kakinuma model for water waves as a higher order shallow water approximation. So please.
Thank you very much for the introduction, and it's my great pleasure to give a talk and to be here, and I'd like to thank the organizers for giving me this opportunity. Last several years, I was interested in this Isobe-Kakinuma model. This is a model for water waves, and this model was derived by the Japanese researchers, Professor Isobe and Professor Kakinuma. They are not mathematicians nor physicists, but they are working in the coastal engineering. And they derived the model equation by using the variational structure of the water wave problem. And Professor Kakinuma, he's one of my friends, and several years ago he asked me how do I think their model from the viewpoint of mathematicians. And in order to answer his questions, I start this research. This is a motivation of my research. And today, I'd like to present the structure of the Isobe-Kakinuma model, and I'd like to show you that that model is a higher order shallow water approximation. So let me start to formulate the water wave problem. So maybe everyone knows well the water wave problem, so it is not necessary to explain the details, but I just confirm my notation. So we consider the water waves in n+1 dimensional Euclidean space, and we assume the water surface and the bottom are graphs like this. And we denote by h, which is a constant. This is a mean depth. Eta is a surface elevation, and b the bottom topography, and g is a gravitational constant. And as usual, we assume the fluid, the water, is incompressible ideal fluid, and the flow is irrotational. Then the fluid motion is described by the following equations. So here we denote the velocity potential by capital phi. So this Laplace equation is a continuity equation in the fluid region, and this is a Bernoulli's law restricted on the water surface, and this is a kinematic boundary condition on the water surface. And this Neumann boundary condition is a kinematic condition on the bottom. So these are the basic equations for water waves, and this is the starting point of our argument. And here, and in what follows, we use the standard notation of nabla and Laplacian is nabla and Laplacian with respect to the horizontal spatial variables, and nabla and Laplacian with the suffix capital X is those with respect to the whole spatial variables. I use this notation. And we introduce a new unknown function phi as a trace of the velocity potential on the water surface. Then the basic equations for water waves can be transformed equivalently as follows: for eta, surface elevation eta, and this small capital phi. So here lambda is a standard Dirichlet to Neumann operator for the Laplace equation. So nowadays these equations, this system is called the Zakharov formulation or Zakharov-Craig-Slim formulation. Anyway, we can transform the original equation equivalently to this system. Now, let me explain the variational structure for the water wave problem. In 1967, Luke showed that the water wave problem has a variational structure, and his Lagrangian is given by this Lagrangian density. And by using the Bernoulli's law, we can rewrite this Lagrangian density by this. So where rho is the constant density of the water, capital P is the pressure, and P atom is the atmospheric pressure assumed to be constant. So therefore, essentially, his Lagrangian is a vertical integral of the pressure deviation, the vertical integral of the pressure deviation in the fluid region. And this part, of course, can be explicitly calculated, which gives these two terms. And this term is essentially constant. So now let's drop this term. And we denote the other terms by L tilde. So this is essentially the his Lagrangian. And the action is a space-time integral. So now let's take the first variation of this action function. Then we after the integration by parts, we obtain this formula. So this is a volume integral in the water region. These two integrals are surface integrals on the water surface, and this is a surface integral on the bottom. So therefore, if we take the first variation with respect to the velocity potential in the fluid region, then we recover the Laplace equation, the continuity equation. And if we take the first variation with respect to the surface elevation eta, then we obtain the Bernoulli's law restricted on the water surface. And if we take the first variation of the trace of the velocity potential on the water surface, then we obtain the kinematic boundary condition on the water surface. And finally, if we take the first variation of the trace of the velocity potential on the bottom, we obtain the Neumann boundary condition on the bottom. So the corresponding Euler-Lagrange equation is exactly the same as our basic equation for the water wave problem. And Professor Isobe used this Lagrangian, this Lagrangian to derive his model as follows. And in 1994, Professor Isobe derived his model by approximating the velocity potential in Luke's Lagrangian by this. Here, Psi is an appropriate function system with respect to the vertical spatial variable, which may depend on the bottom topography. So we should give this function system. And here, this is just a coefficient, and this coefficient becomes a known function. So now, plugging this approximation into Luke's Lagrangian, then we obtain the approximate Lagrangian with respect to these unknown functions, surface elevation, and this coefficient, phi0, phi1, blah, 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 p capital N. So their model is the corresponding Euler-Lagrange equation for the approximate Lagrangian. And Professor Kakinuma extended this method to the internal waves. And since then, he made so many numerical simulations by using their model. Okay, so now the problem is what is the best choice of this base function, Psi. In the case of the flat bottom, in 1872, Buzinesq gave this formula, where P0 is the trace of the velocity potential on the bottom, not the surface, but the bottom. This is nothing but the Taylor approximation of the velocity potential with respect to the vertical spatial variables around the bottom. And here we only have the term of even degree, not contain the odd degree, just even degree. And in this formula, we can explicitly write down the coefficient with respect to this phi naught, but they put these coefficient unknowns. This is an important point in order to derive their models. And for the general bottom topography B, we do not have such a simple expression, but a little bit complicated expression like this. Now, here what I'd like to say is that in such a general case, we not only have the term of even degree, but also have the odd degree, the term of odd degree. So these considerations suggest us that in the case of the flat bottom, it is sufficient to take the polynomial of even degree in our base function. And in the general bottom topography, we should add the term of the polynomial of odd degrees. But I'd like to treat the both case at the same time. So let's take our base function as follows. Let P0, P1, blah, 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 P capital N be integers satisfying the following ordering. And we approximate the velocity potential capital phi by this polynomial with respect to the vertical spatial variable. So this is the coefficient which is unknown. And practically, Pi is the even integers in the case of the flat bottom, and Pi is equal to 1 in the general case, the case of variable bottom topography. And now, plugging this approximation into Luke's Lagrangian L tilde, then we obtain an approximate Lagrangian for unknowns eta and this coefficient. And it is not so difficult to calculate explicitly this approximate Lagrangian, and the result is as follows. A little bit complicated, so for the moment the explicit form is not so important. What I just want to say is that we can explicitly calculate it as follows. And just please memorize that I use this notation, capital H, which is the local dips at a point x at time t. So this is not constant. This is also unknown function. So now it is not so difficult to calculate the Euler-Lagrange equation. And the equations are as follows. Again, a little bit complicated, so I should explain these equations. If we take the first variation of phi I to the approximate Lagrangian, we obtain this first equation. This is an evolution equation for eta, surface elevation eta, and it contains up to the second order spatial derivative of phi j and up to the first order spatial derivative of eta. And index I move from 0 to capital N, so we have capital N plus 1 evolution equation just for one unknown eta. And if we take the first variation of the surface elevation eta to the approximate Lagrangian, then we obtain this second equation. This is just one evolution equation for unknowns phi 0, phi 1, blah, 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 phi capital N. Just one evolution equation for capital N plus 1 unknowns. And this contains the up to the first order derivative of Pj, and it does not contain any special derivative of eta. So this as one of the Isobe-Kakinuma model for our choice of the base function. And now we consider the initial value problem for this Isobe-Kakinuma model under this initial condition. And before giving our existence theory for this initial value problem, let me explain the structure of this Isobe-Kakinuma model. So to this end, let's consider the case where the bottom is flat and putting C, which is just the least scale of Pj, and then the linearized equation around the trivial flow have the following form. This is a time derivative, so this is a spatial derivative. So here, vector 1 is a vector whose components are all 1 here. And here, this is a constant, positive constant, and this is a second order partial differential operator defined by this. And here, A0 and A1 are matrices given by this. So A0 is positive and A1 is non-negative. So therefore, the dispersion relation, linear dispersion relation of the Isobe-Kakinuma model is given by this determinant. Here, where Z is a wave vector and omega is the angular frequency. And A here, this diagonal part comes from this operator, and this is a symbol of this operator. And the off-diagonal part comes from this part. And we can expand this dispersion relation, and we obtain the following formula. We obtain this formula. This is nothing but the quadratic equation, simple quadratic equation for omega. And here we use a new notation, A tilde. A tilde is constructed from the A by this relation. So now, concerning these two determinants, we have the following proposition. For any Z which is not equal to 0, this symmetric matrix A is positive. But if Z is 0, then this matrix has 0 eigenvalue. And concerning this determinant is strictly positive. This is not symmetric, but the determinant is strictly positive. And this determinant divided by Z square is a polynomial in Z square of degree capital N, and the coefficient of the top term is given by this determinant. And concerning this determinant is also polynomial in Z square of degree capital N, and the coefficient of the top term is given by this, both of positive. So anyway, these two determinants are always non-negative, so the solution of omega is always real, so we can define the phase speed as follows. The phase speed is given by omega divided by the wave number, and which is given by this formula. And I denote by this phase speed by Cik. On the other hand, the phase speed of the full water wave problem is given by this, which is well known. So let's compare these two phase speed. So by our proposition 1, we see that this is just one remark, that in this limit, this phase speed converges to this one, which is not 0, whereas the same limit of the phase speed of the water wave problem converges to 0. This limit corresponds to the deep water limit. So this suggests us that the Isobe-Kakinuma model may not be so good model for the deep water. But as we will see, as a shallow water model, it's really nice approximation. So this result was, we obtained this result in the joint work with my former student, Ryo Nemoto. And now let's consider the case where the bottom is flat and we choose Pi as even integer. Namely, we approximate the velocity potential as follows. Then the square of the phase speed of the Isobe-Kakinuma model is the 2n per the approximate of the square of the phase speed of the water wave problem. More precisely, there exists a constant c depending only on capital N, such that we have this estimate. So this is the error, and h times wave number is the ratio of the mean depth to the wavelength. So this is, roughly speaking, this is a shallow water parameter, and the order is 4n plus 2. It's really high order. So, therefore, this theorem gives that at least in the linear case, Isobe-Kakinuma model gives very high shallow water approximation. And now, in the case of the variable bottom topography, we have to add the odd degree, the term of odd degree. In that case, we do not have such a beautiful relation anymore, but still have the following relation. So again, this term is really higher. So this, roughly speaking, this theorem says that, excuse me, if we add the term of odd degree to this approximation, then the order of the error doesn't change. The order of the error is determined only from the term of even degree. So, okay. Anyway, this is a linear analysis. So now let's go back to the nonlinear problem. So this is a nonlinear equations. So as is well known that the water wave problem has conserved energy. The total energy is the kinetic energy plus the potential energy. And the Isobe-Kakinuma model has also the conserved energy, which is defined by this. So this is almost the same as the energy of the water wave problem. We just replace capital Phi by our approximation. So this part corresponds to the kinetic energy, and this part corresponds to the potential energy due to the gravity. So in fact, for any smooth solution of the Isobe-Kakinuma model, we have a conservation of this energy. So Isobe-Kakinuma model has a conserved energy. And until now, I just present just nice properties of the Isobe-Kakinuma model. But it has a really serious drawback. Maybe you can easily see. We can write the Isobe-Kakinuma model in the following matrix form. So this is the only special derivatives, and this is a time derivative, and this is the coefficient of the time derivative. And this coefficient always has a zero eigenvalue. This means that the hypersurface T equals 0 is a characteristic in the model. So this means that the initial value problem cannot be solved in general. In fact, if there exists a solution of the Isobe-Kakinuma model, we have capital N plus 1 evolution equation for eta from this, we can easily eliminate the time derivative of eta, and we obtain the capital N, in a sense, independent relations, which does not contain any time derivative. So in order the existence of the solution, the initial data must satisfy these conditions. And so now we have a question. If the initial data satisfy this condition, can we construct the solution of the Isobe-Kakinuma model? And the answer is yes, but we also need another condition. It's called the sign condition, and it is well known that the well-posedness of the initial value problem for the full water wave problem may be broken unless this sign condition is satisfied, where P is the pressure and capital N is the unit outward normal vector. And since P is constant on the water surface, so this is equivalent to this one. So let's translate this condition in terms of our variable. To this end, we need to specify this capital phi. In order to do that, we use Bernoulli's law. This is a Bernoulli's law. So now, in this Bernoulli's law, we just replace capital phi, our approximation. Then we can calculate the approximate pressure by this relation. So now, let's calculate this quantity for this pressure, approximate pressure. Then, a little bit complicated, but anyway, we can write down explicitly in terms of our variables. So here we have G. So if G is positive and if the solution is small, the positivity is automatically satisfied. But in generally, we do not know that this is positive or negative. So in the rest of the talk, we assume that initially the A is positive. So now one of our results is as follows. Let G, H be positive, and if the initial data and the bottom topography satisfies the necessary condition, and this this is a regularity condition, this is a positivity of the dips, and this is a sign condition. And under these conditions, the initial value problem for the Isobe-Kakinuma model has a unique solution satisfying these in these function spaces. So before 2015, he was also my former student. We also show that in the case of the special case, so this is a generalization of our previous result. So okay, the initial value problem is well posed. The problem here, we have some question. How do we prepare the initial data which should satisfy the previous condition of this? Otherwise, the solution does not exist. So how do we prepare the initial data? Because eta is a physical meaning, but phi j has not physical meaning, just a coefficient. So now let's go back to the Zaharoff-Craig-French formulation. Let phi as a trace of the velocity potential on the water surface. So I think that nobody has an objection to give the initial data for this phi. And the relation of this phi and our variables is as follows. So now we give the initial data for phi, this phi, and this relation and the previous necessary condition uniquely determine the initial data for the Isobe-Kakinuma model. So this proposition says this statement. So we can prepare reasonably the initial data. Okay, the well-posedness is now okay. So now let's move to the shallow water approximation. So to this end, let's rewrite the equations in the non-dimensional form.
May I,
Yes.
may I make a comment?
Yes.
Please go back to the previous slide. Yeah. No, the next one. You give phi, and you determine phi I
Yes.
by that relation.
Yes. Well, uniquely.
Uniquely, but it's a coefficient matrix is a Hilbert matrix, and the inversion of Hilbert matrix is a very ill-posed numerically. Mathematically, it is guaranteed. So numerically, it has a very serious problem. So I don't know how Kakinuma dealt with this one, but numerically, it's, I think, very serious problem. So because small error is magnified tremendously from phi to phi I.
But how to say this? Maybe you think that if we use this exact relation, maybe you think that this exact relation.
But that is again expansion by the polynomials in x squared, x third, and so on. Yeah. Numerically, it's not well posed.
But a little bit because we take the variation, this relation doesn't hold. A little bit change, and the equation becomes just the elliptic equation, and the denominator is positive definite. So I guess that numerically it's not so unstable. So I think that a little bit difference between the exact relation, but our relation.
But there are some elliptic equations. It is positive, but inversion is very difficult because the bad choice of the base. Okay, so elliptic equation is okay. But if you use very bad base functions for numerical computation, then it becomes very bad. So I'm wondering, you don't agree?
Yeah, no, I agree.
You agree with it. So I'm very curious about how Kakinuma computed.
But
mathematically, it's okay. I believe you, of course.
Yes.
I'm not criticizing you.
Yes.
But I'm asking how they computed.
Okay.
But maybe we could continue on that question after the presentation.
Okay.
So if you can go on, and we can continue the discussion.
Okay. Okay. Thank you very
I
much.
completely agree with you.
Okay. Okay. Later, let's discuss. Okay. Now let's move to the shallow water approximation. Yes. So let lambda to the typical wavelength, and h is the mean depth of the water as before. And we introduce non-dimensional parameter, the ratio of the mean depth, that's the wavelength, which is well known, the shallow water parameter. And we rescale the independent and dependent variables as follows, and plugging this, and we can write our equations in appropriate non-dimensional form. So I do not explicitly write down the non-dimensional form, but just I first consider the linearized equation to the Isobe-Kakinuma model around the trivial flow in the case of the flat bottom. Now let's consider this simple case. So let eta ww phi ww be a solution of the linearized water wave equations, and eta ik p0 blah 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 pn be a solution of the linearized Isobe-Kakinuma model under this choice of our base function. So thanks to our theorem 1, which states the 2n path approximant, under appropriate condition on the initial data, we can show that the solution of the water wave problem can be approximated by the solution of the Isobe-Kakinuma model with the error of this order delta to the power for n plus 2. Here, let's remark that it is well known that the water wave problem can be approximated by the solution of the nonlinear shallow water equations up to order delta square. So this is well known, and then this is established. And also we have the so-called the Green-Naghdi equation. Green-Naghdi equation is known as the higher order shallow water approximation. And the solution of the water wave problem can be approximated by the solution of the Green-Naghdi equation up to the error of order delta to the power 4. But here in our case, even in a simpler case, n equal to 1, this is a simpler case, the error is higher than the Green-Naghdi model. So this suggests that the Isobe-Kakinuma model is really a higher order shallow water approximation. But this is a linear theory. How about the nonlinear theory? But before talking about this, let's remark the advantage of the Isobe-Kakinuma model. So now we show that initial value problem is well posed, and at least in the linear case, this is a higher order shallow water approximation with an error of order delta to the power for n plus 2. And one of the important feature of the Isobe-Kakinuma model is it does not contain any higher order derivatives. Usually, if we try to obtain the higher order shallow water approximation, usually it contains a higher order derivative. But in the numerical calculation, maybe you agree, the higher order derivative is troublesome. So we do not use such a higher order derivative. But Isobe-Kakinuma model is just the second order PDE, the system of second order PDE. And in the derivation of the Isobe-Kakinuma model, we do not assume any weakly nonlinearity. Therefore, it may hold for the strongly nonlinear regime. But for the moment, it is expected. And it is ongoing research. But just today, I'd like to report that in some simpler case, it is true. So Isobe-Kakinuma model is a higher order approximation even in the strongly nonlinear regime. So now, to state our result, let's consider the following simpler case where we assume the bottom is flat and we adopt this approximation. So just capital N is equal to 1. So the simplest case. So then the Isobe-Kakinuma model in the non-dimensional form has this form. Here we have the non-dimensional parameters. And we have two evolution equations for eta. And we have just one evolution equation of phi naught and phi 1. Here capital H is the local dips at point x at time t. So it is a non-dimensional form, so the mean dips is normalized just 1. And we impose the initial condition as follows. And now the necessary condition for the existence of the solution is easily obtained by eliminating this time derivative of eta. And the result is follows. This is a necessary condition for the existence, and which is equivalent to this simple equation. And now let phi be the trace of the velocity potential on the water surface, as before. So So this relation, in terms of our variables, this quantity phi can be written as this. This just comes from this relation. By taking the trace of this relation on the water surface, then we obtain this relation approximately. So now our result concerning the shallow water approximation is, before giving our result, I should mention the existence theory for the full water wave problem. So the full water wave problem in the non-dimensional form can be written as follows. So we have a non-dimensional parameter delta. So lambda corresponds to the Dirichlet-Neumann operator. So the existence and the uniform bound of the solution of this full water wave problem was given by myself and Samaniego and David Lang. So we have the existence theory for the full water wave problem. So now let's compare the solution of this full equation and the solution of the Isobe-Kakinuma model. So the theorem is as follows. A little bit complicated, that essentially is as follows. Suppose delta is a shallow water parameter, is sufficiently small, and initial data, this initial data is the initial data for the full water wave problem. Satisfy this regularity condition, and the dips is uniformly positive. So this is very natural condition. And if we assume the sufficiently small delta, the sign condition is automatically satisfied. So we did not specify, we did not give such a condition. This condition is automatically satisfied. Then the necessary condition and our relation determine uniquely the initial data for the Isobe-Kakinuma model. Now let eta, as before, let eta WW phi WW be the solution of the initial value problem for the full nonlinear water wave problem, and eta ik phi naught phi 1 be the solution of the initial value problem for the nonlinear Isobe-Kakinuma model, and define phi ik by the previous relation, this. By using this relation, we define phi ik in terms of the variable of Isobe-Kakinuma model. So this, in order to construct this solution for the Isobe-Kakinuma model, we use this initial data. We should use this initial data. Then, for any delta, we have this error estimate. The solution of the full water wave problem can be approximated by the solution of the Isobe-Kakinuma model up to order delta to the power 6. The linear analysis say this order. So in the nonlinear case, it holds. I have some time. So finally, let me explain the idea how we show our existence theory and this the theorem for the shallow water approximation. So the serious drawback is that the hypersurface T equals 0 is the characteristic. So we cannot solve in general. So we have to transform the equation to some system for which the hypersurface T equals 0 is not a characteristic. We should do that. How do we do that? The idea is very, very simple. So to explain the idea, let's consider the case of the linearized equation around the trivial flow. So the equation can be written in the matrix form, and we denote each column of this matrix operator like this. then we can rewrite the linearized Isobe-Kakinuma model as follows. We have just one evolution equation for eta. We have capital N plus 1 evolution equation for eta. So just one evolution equation for phi, and we have N plus 1 evolution equation for eta. So the necessary condition comes from this, just by eliminating the time derivative of eta. So this is a necessary condition. So now let's take the time derivative of this necessary condition. And then we have this relation, capital N relation. And we also have this equation. This is also an evolution equation for phi. So now we have capital N plus 1 evolution equation for phi. Phi consists of the N plus 1 unknowns, so it's okay. And these two equations can be written in the matrix form like this. And here, the symbol of this operator, the determinant of the symbol of this operator is strictly positive, as explained before. So therefore, there exists an inverse of this operator. And the inverse operator, it's anymore the differential operator, but the pseudo differential operator. But it can be written in this form, and it should satisfy this relation. And now let's take the inverse of this operator. Then we obtain this relation. And now we apply the positive operator A from the left-hand side to this equation, and using this relation, we obtain this equation. So this is very nice equation for phi, which has a good symmetry. And how which equations should we use for eta? Because we have N plus 1 evolution equation for eta. Which one is the best one? As a result, we should use everyone. Namely, we should take an appropriate linear superposition of this equation. How do we choose the coefficient? We use this coefficient, Q. Then, so this is capital N plus 1 evolution equation for eta in the matrix form. And applying this operator and using our relation, we obtain this one. This is an evolution equation for eta. Now we obtain the evolution equations. And in the matrix form, it has this form. So here, this is a positive definite. Here, here CIK, so I defined before this notation. This is the phase speed of the Isobe-Kakinuma model. So the symbol of this operator is this one. So this is normal differential operator. But anyway, this is a symmetric. Lambda is also symmetric. The coefficient is antisymmetric. So this operator is an antisymmetric operator. This is a symmetric operator. So we can symmetrize the equations. So now we can apply the standard technique of the PDE. But the problem is, this is not PDE. This is a pseudo differential operator. How do we treat this? The strategy one is that as z goes to infinity, this converges to some positive constant. So modulo of lower order terms, we can replace this one to the constant, modulo lower order terms. So the strategy one is use this structure. So this is a symmetric form of the Isobe-Kakinuma model, and this is a lower order term, and this is differential equation. So we can apply the standard theory for the existence of the solution. But in order to show the shallow water approximation, if we use this strategy, we cannot obtain the uniform bound of the solution. So we should not use this one. But in that case, so this is not the differential operator, but denominator and the numerator are both polynomial. So if we apply the differential operator whose symbol is this, then this becomes the differential operator. So the strategy is to this one. So this is again the differential operator, and this is a anti-symmetric operator, and this is a symmetric operator, but this is a higher order. It contains a higher order derivative. And by using this symmetrical form, by using this symmetrizer, we can obtain the uniform boundness of the solution of the Isobe-Kakinuma problem, and we can show the rigorous justification of the Isobe-Kakinuma model. Okay, thank you very much for your kind attention.
Thank you very much. So we have some time for discussions.
Question.
Yes.
So in your condition 7, I think you have a condition 7. I'd like to see it again. That you call it.
Yes.
That you said you need to be able to solve this to get the initial condition, something like that, going. Is that right?
Yes. Not only this is a this is a system of second order PDE, but unknown, we have capital N plus 1 unknowns, and this is a capital N equation, so it's not sufficient. We need to another equation to solve this equation. And another equation is this one. So if we add this equation to the previous necessary condition, if we give this phi, we can solve uniquely this quantity phi I. So we can solve.
But this is in the condition, so you mentioned something which was discussing about the condition. This is like at the initial time?
Yes.
So can I say, is it correct to say that it's almost like checking if with your initial data and with the base you've chosen,
yes,
you can sort of do like at time 0 an approximate or a good harmonic extension of your data and then follow on? Is that sort of what's going on, or do I get it wrong?
I do not understand the
Because
point.
you mentioned about the trace, so it's over there, the trace,
Yes.
right? You
Yes.
have this basis, you need to get coefficients to represent your function. Is it, so it's almost like I wrote down here, is it almost like you were mentioning about the initial condition, or is it correct? In my mind it's like that, maybe I got it wrong. It's like an initial constraint
Yes.
within your function of approximation, though maybe I can see from your expression that maybe I haven't got it right, so I just like to double check. That's okay. I'll think about it more. And the other thing that I find it interesting is that in the formulation, when I bring the Jewish state to normal map with bottom topography, and we have an ansatz that's inspired by what Craig, Guillen, Nichols, and Sulem were doing, where they add to the hyperbolic cosine, say harmonic extension of Fourier modes in the depth for the flat bottom, and that gives you the hyperbolic tangent symbol for the Jewish state normal map. Then they add as an ansatz the hyperbolic sign with undetermined coefficients, blah blah blah, and that's how we follow. And in my mind also, hopefully I got it right, maybe I got it wrong, is that the hyperbolic cosine expansion, I mean, if you expand hyperbolic cosines, you get the even powers that of like a polynomial approximation. And the hyperbolic sign in the ansatz that Craig and company do is probably an analog of your odd terms.
Yes. Yeah, of course. Yeah. Yes.
In the expansion of
Because so. Excuse me. Here, so there are many choice of the base function. Yeah. Again, you correct. The hyperbolic cosine. I think hyperbolic cosine is one of the choice of this base function.
Which are related to the even terms, I think.
Yeah. And but
when you add the
yeah,
odd terms, you're basically invoking the
but
approximate sign.
but for me, I think the polynomial is better in the case with the bottom. In the case of the deep water, no, we cannot use the polynomial, so we should use the exponential. But in the case of the with the bottom,
No, but again, yeah, but in particular, in the case of shallow water, then expanding these guys,
it's essentially
h is small.
but the difference is so this is essentially the Taylor approximation.
Yes, right.
And so you mentioned that this is essentially the harmonic expansion.
Yeah, this is basically, but somehow the Koch is in there, right?
No, this is entirely different.
Or is it different?
It's much more reversed the other way. So this is a very severe restriction, these expansions.
Yeah, no, these expansions, like you see it, yeah.
Yeah.
And
You see what you get.
but in the case of if we use a harmonic expansion, we should restrict the periodic boundary condition in the horizontal spatial barriers in order that the base function should be discretized.
Maybe you should continue during the coffee break on this discussion. Is it other questions, maybe? There is one in the back.
Finite Rock results for that equation.
This is a fully nonlinear case, so I expect that in generally the finite time blow up occur, but I do not know the exact theory.
Yes, please.
You started out with Zakharov's formulation.
Pardon?
You began with Zakharov's variables. The variables for the Zakharov formulation of the water wave problem.
The Sakharov formulation.
Sakharov.
Yeah, the first slide.
Zakharov, excuse me.
Put it up.
There's no reason.
Yes. Yes.
You began with Zakharov's formulation, and Zakharov's formulation is a Hamiltonian system.
Yes.
So it has variational structure.
Yes.
But then you switch to a different derivation of the equations, which has nothing to do with the Hamiltonian structure.
No.
And my question is, why did you do that? That's the first thing. And secondly, what role does the variational structure have in the subsequent theory? Does it guide anything? Or could you have done this without the variational structure?
Why? As I told in the beginning of my talk, the motivation of my research is to answer the question given by the Professor Kakinuma. And Professor Kakinuma and Professor Isobe derived this model. Here, in the beginning, I do not know why they derived this kind of model equation. So at that time, we do not find out a good reason. So therefore, in the beginning, I thought that this model should be wrong. Maybe the Green-Naghdi model is much better, I thought. But in order to explain, in order to confirm, I calculated. But the result is completely different, opposite, very good. So
if you retain the Hamiltonian structure,
Yes.
in the simple case of a flat bottom, the Hamiltonian system can be written as a Hamiltonian system for two functions,
Yes.
phi and eta,
yes,
and the Hamiltonian system is quadratic
yes,
with no higher order terms, so there's no approximation needed to get a quadratic equation for a quadratic differential equation for the full system on a fixed domain. This is in Zakharov's paper.
excuse me.
I think you have to think about that. Now the time is up, so I think we have to conclude, and thank you once more. Thank you very much.
Thank you very much.